The next topic is evaluating U, H, and S for ideal gas mixture. So in this chapter, we will have a situation where the system with a mixture as the working fluid conducting a thermodynamic process, and we need to apply a conservation of energy. So to apply the conservation of energy principle to a system involving an ideal gas mixture requires an evaluation of the internal energy, so U, enthalpy, H, or specific heat, so Cp, Cv, or K, of the mixture at various states. So similarly, to conduct an analysis using the second law of thermodynamics normally requires the entropy of the mixture. So for an ideal gas mixture, the values of U, H, and S are evaluated by adding the contribution of each component at the condition at which the component exists in the mixture. So you will see in the next slide how is U, H, and S defined for an ideal gas mixture. The first equation here, equation 12.17, is the internal energy of the mixture. It is defined as the sum of the internal energy of component 1 plus internal energy of component 2 and so on through internal energy of component J, and it can be written in compact form here by using a summation sign here. So the sum from I equal to 1 until J of Ui. So Ui is the internal energy of component I. And then the second equation here is for enthalpy. So similarly, the mixture enthalpy is the sum of the enthalpy from component 1 plus component 2 through component J. And we can also write it down the equation in a molar basis. So the first question here, equation 12.19. So this is the specific internal energy per unit molar. So you can see in here we have upper bar here. So the unit for this parameter will be either kilojoule or joule per kilomole. Okay. And then N here is the number of mole. So N, this is the total moles of the mixture, time U, this is the specific internal energy in molar basis of the mixture, equals to N1 times U1, U over bar here. So this is from component 1, and then this is from the component 2 and so on through component J. And we have a compact form, this one. And then similarly, we have equation 12.20 for the enthalpy in molar basis. So this is N, so the total moles of the mixture, times H over bar. Here is the specific enthalpy in molar basis, equal to the multiplication of N1 times H1 from component 1, and then this component 2 through component J. And then if we divide each term in equation 12.19 and equation 12.20, I saw the equation in this bottom right. So you will get the expression for the specific internal energy and enthalpy of the mixture per mole of mixture. And you will get equation 12.21 and equation 12.22. So this is for the specific internal energy and this is for the specific enthalpy. So this is per mole of mixture. So what is important here, now you have Y here. This is the mole fraction. So U, specific internal energy of the mixture, is the sum for all components, so from component I through component J, so Yi, so this is the mole fraction of component I times the specific internal energy of the component I. By differentiation of equation 12 12.21 and 12.22. The equation is shown at this bottom right. With respect to temperature, will result in these two equations. So first one is equation for Cv, second one is the equation for Cp. So specific heat at constant volume, second one is specific heat at constant pressure. And you remember in thermo 1, the definition of U, it's equals to Cv times T, and then H equal to Cp times T. So if we differentiate equation 12.21, you will get equation 12.23. So you can see in here that Cv of the mixture is the sum of the multiplication for mole fraction times Cv of the component I. Okay, so I is from 1 through j. And similarly, if we differentiate equation 12.22, so this is for the enthalpy, you will get equation 12.24. So you can see in here that Cp of the mixture is the sum of yi times Cpi. So this is I from 1 through j. So the mixture specific heat Cv and Cp are mole fraction average of the respective component specific heat. So once again, equation 12.23 and 12.24. The next one is for the entropy. So the entropy of the mixture is the sum of the entropy of its components. So you have equation 12.25. So S equals to S1 plus S2 through Sj. And we have a compact form here. So S is the sum of all component entropy. So here is I, and then I from 1 through j. And then we can also write it down this equation in molar basis. So we have equation 12.26. So n time small s bar here is actually S capital here. Okay, so n times s equal to n1 times s1 plus n2 times s2 and so on through nj times sj. Okay, and then if we divide each term in this equation 12.26 by the total number of moles of mixture, and this is n, then you will get equation 12.27. So you can see in here that the entropy of the mixture is the sum of the multiplication of the mole fraction times the entropy of the corresponding component. So the component here is from component I through component j. This table is showing the property relations on a mass basis for a binary ideal gas mixture. So binary, so it's mean it has two components. So in this case is gas 1 and gas 2. So M1 is mass of gas 1 as well as M2 for gas 2. And then M capital 1 here is the molecular weight of component or of gas 1, and then M2 is the molecular weight of gas 2. And then we have M, small m here is the mixture mass, and then this is the sum of M1 and M2. And then we have MF1 here, this is the mass fraction. Okay, so this is M1 over M, and then MF2 is M2 over M. And then we have T is the temperature, pressure is P, and then capital V is the mixture volume. For this binary gas mixture, so we have equations of state here. Equation A, so this is P is the mixture pressure, and then M is the total mass of the binary mixture, and then R with over bar here is the universal gas constant, and then T, V is the pressure and volume respectively. So M here is the apparent or average molecular weight of the binary mixture. So it is defined with this equation. So you can check it in the previous slide. So M equal to Y1 times M1 plus Y2 times M2. And then the mole fraction Y1 and Y2 are given by equation B here. So for example, like Y1 equals to N1s over N1 plus N2. Similarly, Y2 is N2 over N1 plus N2. Okay. And then we have also this correlation already in the previous slide. And then partial pressure P1. So this is the multiplication of mole fraction of gas 1 times mixture pressure. So you also have P2 here equals to Y2 times P. And then for the properties on a mass basis, we have equation D here. This is for the mixture enthalpy. So capital H. So equals to M1 times H1 plus M2 times H2. And the enthalpy here is only a function of temperature. Okay. And then the second one here, equation E, this is for the internal energy. So U equal to M1 times U1 plus M2 times U2. And this is also a function of temperature only. And then we have Cp here. So Cp equal to M1 over M times Cp1 plus M2 over M times Cp2. Okay, so it has slightly different formula here for Cp. So Cp here is the mass fraction times the Cp of the corresponding component, and then plus similar or same form, same term for the second cases. And then Cv, this is formulated similar to Cp. So this is the mass fraction times Cv1 plus the mass fraction of gas 2 times Cv2. And then the last one here is for entropy. Entropy formulation is similar to internal energy and enthalpy formula. So this is M1 times S1 plus M2 times S2. But you can see in this last equation inside the bracket here, there are two parameters. So it's mean to determine the entropy of gas 1, we need two properties. So in this case, temperature and pressure, or maybe temperature and specific volume. And then by using the molecular weight of the mixture or of component I as appropriate, data can be converted from a mass basis to a molar basis or conversely. So you have this correlation. So M here is the mass equal to molecular weight times N. Okay, so using this correlation, we can convert molar basis to mass basis or conversely. For the mixture, we have equation 12.28. So in this case, the specific internal energy of the mixture on molar basis equals to the molecular weight of the mixture times the specific internal energy of the mixture on mass basis. Okay, similarly, you have this equation for the enthalpy, Cp, Cv, and S. Okay, and then for the component I, you have equation 12.29. So for example, in here, the specific enthalpy of component I on molar basis here equals to the molecular weight of component I times the specific enthalpy of component I on mass basis. And then to perform thermodynamic analysis of system involving non-reacting ideal gas mixture, I put a stress on this non-reacting because we will have another case with reacting in the next chapter. So for this non-reacting ideal gas mixtures required no new fundamental principle. So it's mean the conservation of mass and energy principle and the second law of thermodynamics are applicable directly. And then evaluation of the specific internal energy or specific enthalpy of a mixture component I requires only a single intensive properties. In this case, it's temperature. So it's only required single properties, and in this case, temperature. Therefore, you can use table A22 for estimating the, for example, the specific internal energy or specific enthalpy of air or other component in table A23, and it's only a function of temperature. And then evaluation of the specific entropy of a mixture component I requires two intensive properties, and I did mention in the previous slide. So in this case, we will use the mixture temperature T and the partial pressure Pi to determine, for example, the specific internal energy of component I. Next one is mixture processes at constant composition. So on the right side is showing a schematic of the system with a mixture as a working fluid at the state 1. So we have a system here with a temperature and pressure T1 and P1, and it consists of N1, N2 through Nj. So this is the mole numbers of component 1 through component J. And then it undergoes a process, and this process occurs at constant composition, so no change of the composition. And then it goes to state 2, and at state 2 the pressure and temperature is T2 and P2. Okay. And then from the previous slide, you know the formula of the enthalpy and then internal energy and entropy at state 1. Okay, and this one is the formula of similar parameter at state 2. So you can see, for example, U2 here is the sum of Ni times Ui at T2, and this is for component 1 through component G. So the change in internal energy and enthalpy of the mixture during the process are given by equation 12.30 and 12.31. So this case U2 minus U1, you just replace U2 and U1 by this equation, this one. And then you will get equation 12.30. And similarly, for H2 minus H1, you have equation 12.31. Dividing by the number of moles of mixture N on each term of equation 12.30 and 12.31 will result in equation 12.32 and 12.33. So you can see here that now on the left side you have a delta U, and U in small letter. So this is the delta U specific internal energy on molar basis. Okay, and then you have also delta H. H is small letter here, equation 12.30. So this is the change of the specific enthalpy on molar basis. Similarly, the change in entropy for the mixture is given by equation 12.34. So S1 minus S2. So you just replace S2 by this formula, and then S1 by this formula. And then if we divide each term on this 12.34 by the number of moles of mixture N, so you will get equation 12.35. So delta S, as here is small letter, so this is specific entropy, equals to this equation. So you see here we have Yi, so this is the mole fraction. The mole fraction multiplied by Si at state 2 minus Si at state 1. Why we can use this formula? Because the composition is constant. So it's mean yi at state 1 equals to yi at state 2. We will still use case tables in this chapter. So for several common cases model as ideal cases, we have table A22 and table A23. I believe you are very familiar with table A22. So this is for air and gives you the quantities on a mass basis. And then table A23, you can open the corresponding table. It has a different variety of gases, and it gives you the properties on a molar basis. And then for entropy, we will use the formula introduced in chapter 6, I believe, in THERMO 1, and it's shown here, but it is for component I. So I believe the original formula for delta S is that delta S equal to S2 minus H1 times R over bar, so this is universal gas constant, times ln P2 over P1. And then for this ideal gas mixture, the delta Si, so this is for component I, equals to Si at T2, but this one, oh yeah, I forgot to mention, they have a degree sign here. So, and this value is available either in table A22 or A23. So Si at T2 minus Si at T1 minus R with over bar time length Pi2 over Pi1. And then since the mixture composition remains constant, we have this relationship. So Pi2 over Pi1, so you can replace Pi2 as Yi times P2. Similarly, we can replace Pi1 with Yi times P1. So it is constant, the composition, so it's mean Yi here cancel out. So you have from the last term here that Pi1 over that Pi2 over Pi1 equals to P2 over P1. Okay, then you can substitute Pi2 over Pi1 by P2 over P1. You will get equation 12.36. See here on the last term, now you have ln P2 over P1. So P2 is the mixture pressure at state 2 and P1 is the mixture pressure at state 1. At certain case, we might assume constant specific heats. If this happens, then the specific internal energy, enthalpy, and entropy change of the mixture and the component are formulated by equation 12.37 and 12.38 and 12.39. So on the first column here, so this is the formula for the mixture, and this one is for the component. For example, delta U with over bar, so this is the change of the specific internal energy on molar basis equals to Cv, so with over bar, so this is also on molar basis, times T2 minus T1. And then next one we have the formula for delta H, and then on the right side we have delta Ui, so this is the change of the specific internal energy for component I, equals to Cvi with over bar, so it is on molar basis as well, times T2 minus T1. And then the last one here is for the change of the specific entropy. Now let's take a look on this example. So this is example 12.3 in the textbook. A mixture of 0.3 pound of carbon dioxide and 0.2 pound of nitrogen is compressed from P1 of 1 atmosphere and T1 of 540 degree Rankine to P2 of 3 atmosphere in a polytropic process. Okay, polytropic process. I think this is in chapter 2 of Thermo 1 when we talk about the first thing of the polytropic process, for which n equal to 1.25. The question, the final temperature in Rankine. Second question, the work in PTU, and then the heat transfer in PTU, and then the last question is the change in entropy of the mixture in PTU per degree Rankine. Let's have a look at the solution of this example. Okay, so in this case, what is known is a mixture with 0.3 pound of CO2 and 0.2 pound of N2, and then P1, T1 is given, and then P2 is also given, 3 atmosphere, and then polytropic process with the polytropic exponent of 1.25. And then the question is the final temperature, heat transfer, and then work and entropy change. On the left side, this is the schematic of the system. So this is a closed system, and the dashed line there is showing the boundary of the system. So it is a binary mixture, so with two components, CO2 and N2. And P1, T1 is given, P2 is also given. And then on the right side, this is the PV diagram. So starting from point number 1 here. So with 1 atmosphere and 540 degree Rankine. And then at state 2, the pressure increases. So it's mean it's doing kind of a compression process. So pressure increases and then volume decreases. And then on the right side is the list of the assumption or engineering model. So this is a closed system. So it's been control mass. And then with a mixture of CO2 and N2. And then the mixture composition remains constant during the compression process. And then we can apply the Dalton model. So in this case, each mixture component behaves as if it were an ideal gas occupying the entire system volume at the mixture temperature. And then the overall mixture acts as an ideal gas. And then assumption number 3, that compression process is a polytropic process with n equal to 1.25, and then we can also ignore the impact of kinetic and potential energy change between initial and final states. The first question is the temperature at the end of the compression process. So this is a polytropic process, and the temperature and pressure at the end state of a polytropic process are related by equation 3.56. So this is chapter 3 in Thermo 1, and equation 3.56 is shown in this slide. So T2 equals to T1 times a P2 over P1 to the power of n minus 1 over n. We have all number for the parameter on the right hand side. You just plug in all the number there. You will get T2 of 673 degree Rankine. The second question is the work for the compression process. So this is a control mass system, so it's closed system. So it's mean W equals to the integral P dV. Okay, please do not confuse with the W for the control volume. So where we have integral V dP. Okay, for the control mass, a closed system. So we have this formula. For this polytropic process, we have this correlation. So P times V to the power of n equal to constant. This constant can be P1 V1 to the power of n, can be P2 V2 to the power of n. So if we substitute P in this formula by constant over V to the power of n and then do an integration, we will have this formula. So W equal to P2 V2 minus P1 V1 over n over 1 minus n. You can review one of an example in chapter 3. I believe there is a similar question about the W. So what will be the W term or W formula for n equal to 0 and then n equal to 1 and then for n above 1. Okay, so we have P2, we have P1, but we don't have V2 and V1. Okay, so to solve this problem, we can convert this formula by the aid of ideal case equation of state, because we know that P times V equal to mRT. Okay, so M is the mass and then R is the gas constant. So this R equal to R with upper bar over the molecular weight. Okay, so if we replace P2 V2 by M times R over bar over M capital here times T2, similarly we can replace P1 V1 by M times R times T1, so we'll have this formula. Okay, and then the mass of the mixture is given, so we have 0.3 CO2, I believe, 0.3 pound CO2 and then 0.2 pound of nitrogen. So the total mass is 0.5 pound. So this is the total mass of the mixture. And then the apparent molecular weight of the mixture can be calculated, right, using this formula. And then N is the total number of moles of mixture. And then we have equation 12.1 to calculate the number of moles for CO2 and N2. So the mole number of CO2 is the mass of the CO2 over the molecular weight of CO2, 44. And then the mole number of nitrogen is 0.2 over 28. So this is the molecular weight of nitrogen. So we have NCO2 of this number and then N2 of this number. Okay, so by summing up these two moles number, so we have the mixture mole numbers of 0.0139 pound. And then we can also now calculate the apparent molecular weight of the mixture, which is the mixture mass 0.5 pounds over the mixture mole number. And we have the apparent molecular weight of the mixture of 35.97. Then now we can calculate the compression work. Okay, so we have all number there, T1, T2, and then the apparent molecular weight and so on. So make sure we apply the unit conversion, okay, from fit pound force to PTU. So you will get the compression work of 14.69 PTU. So this is negative because the work is done to the system. Okay, and then question number 3, it's asking, I believe, Q here. So with assumption number 4, so it's mean we can ignore the effect of kinetic and potential energy. So we can apply the conservation of energy here as Q equal to delta U plus W. And delta U here is the change in internal energy of the mixture. And then we can use this formula to calculate the delta U of the mixture. So this is just the sum of the internal energy change of the components. So in this case we have CO2 and N2. So you can see in here, so this is the mole number of CO2 times the specific internal energy of CO2 at state 2 on molar basis, and then this one is at state 1, and this is for N2. Okay, so this form is convenient because table A23E gives internal energy value for N2 and CO2 respectively on molar basis. Okay, on molar basis, so that you should use this formula. And then you need to open your table A23E. So looking at the specific internal energy of CO2 and N2 at T1 and T2, and then you just plug in the number, you will get delta U of 11.3 PTU. Okay, and then by inserting this delta U and W into this expression, you will get a Q of minus 3.39 PTU. So this minus sign signifies a heat transfer from the system. The last question is the change in entropy of the mixture. So this is equals to the sum of the entropy change of the component. And we have equation 12.34 in the previous slide. So delta S here is the sum of n CO2 times delta S of CO2 on molar basis plus n N2 times delta S of N2 on molar basis. And then delta S N2 and delta S CO2, this is on molar basis, are evaluated using equation 12.36. And then S degree bar for N2 and CO2 can be obtained from table A23 at state 1 and state 2. And then by plugging the number, so you will get this number. So delta S equals to minus 0.0056 BTU per degree Rankine. So this entropy decrease, so this is minus sign here, because entropy is transferred from the system accompanying the heat transfer. Next example, it is example 12.4 in the textbooks. A gas mixture consisting of CO2 and O2 with mole fractions 0.8 and 0.2 respectively expand isentropically and at steady state through a nozzle from 700 Kelvin 5 atmosphere 3 meter per second to an exit pressure of 1 atmosphere. The question, the temperature at the nozzle exit in Kelvin, and then the entropy change of the CO2 and O2 from inlet to exit in kilojoule per kilomole Kelvin. And then the last question is the exit velocity in meter per second. Let's take a look at the solution of this example. So we have a gas mixture. This is a binary mixture. So CO2 and O2 with a specified mole fraction, I believe. And then it's expand isentropically through a nozzle from a specified inlet condition to a given exit pressure. And then the question is the temperature at the nozzle exit, and then the entropy change of the CO2 and O2 from inlet to exit, and then the last question is the exit velocity in meter per second. On the left side is the schematic of the system. So the mixture flow from left to the right. So the specified inlet condition is given in the schematic, velocity, pressure, temperature, and then at the exit the pressure is given 1 atmosphere. And then on the right side is the TS diagram. So assuming it is an isentropic process, so it's mean constant entropy. So state 1 to state 2 is connected by a straight vertical line in this TS diagram. And then this is the assumption or engineering model. So it is a control volume, and then steady state, and then the mixture composition remains constant. And then we can use the Dalton model, and then we can ignore the change or the impact of the potential energy between inlet and exit. Okay, the first question is the temperature at the exit. So the temperature at the exit can be determined by using the fact that the expansion occurs isentropically. So it's mean there is no change of the entropy. So S2 minus S1 equal to 0. And then as there is no change of the specific entropy of the mixture, then we can use equation 12.35. And then in this case, we can simplify to get equation A here. So S2 minus S1 equal to the delta S of O2 times the mole fraction of O2, and then plus the delta S of CO2 times the mole fraction of CO2 equal to 0, because S2 minus S1 equals to 0. And then the composition remain constant, and then the ratio of partial pressure equal to the ratio of mixture pressure. Okay, and then accordingly the change of specific entropy of each component can be determined using equation 12.36. okay, and then equation A here can be rewritten to have this equation. Okay, we just need to replace the delta S for O2 and CO2 by the formula from equation 12.36, and it is written here. This is for O2 and then this is for CO2, and the original term for the Ln here is the ratio for the partial pressure, but because the composition remains constant, we can replace this partial pressure ratio by the mixture pressure ratio. And then we can arrange the equation to be like this one. Okay, so it's a bit long equation here. And then the sum of mole fraction for sure equals to unity. So the coefficient of the last term on the right side, so this is this one equals to 1. Okay, and then we can grab the data of S degree here for O2 and CO2 at this temperature from table A23. So this one can be from table A23, this one also can be from table A23. Okay, and then if you plug in the number of the S degree at T1 for O2 and CO2 along with this simplification, then you will get this correlation. Okay, and then you can simplify it as this one. Okay, so you have an equation here, and then on the first term on the left side, this is SO2 at T2, and then the second one here we have SCO2 at T2. Okay, so with this equation we need to do an iterative approach. Okay, so first you need to guess what is temperature of T2, and then you go to table A23 to get what is S degree for O2 and CO2 at the gas temperature. Okay, and then you plug in the number there, and then you can check it whether it's really equal. The best way is you grab maybe one extreme value and the other one is one extreme value from the other side, and then you can do a kind of numerical method there. I'm not sure whether you already taken numerical method when you take this THERMO 2, and then you can use a method of bracketing method to get the correct T2. But otherwise you can do a simple manual way. Take arbitrary temperature. Okay, you can start even with T1 and then calculate it, and then you can see the trend. For example, if the number is too low, then you need to increase it. So you can increase it gradually, maybe pick up number, I don't know, increase by, let's say 100, and then check whether you already get the number on the other side, and then from there you can determine what should be the correct one. So in this example, it takes first temperature of 510 Kelvin, and then the second one is 520 Kelvin. Okay, and then this two number is already on the other two extreme. So one's result in too low value and the second one result in too high value. So in this case, the correct one will be somewhere between 510 and 520. And then by doing kind of interpolation, you will get this one. Okay. You can give it a try. I know you can use your Excel, which will give you a faster result, but I believe for having this problem in the exam, it might take a time, and very probably it won't be in the exam. So far we have considered a case where the mixture has been formed already. So in this example we will have a look for the case of the mixing process. So the mixing process is an irreversible process because the mixture can form spontaneously, but to separate the species from the mixture would require an energy from the surrounding. Okay, this is also example 12.5 in the textbook. Two rigid insulated tanks are interconnected by a valve. So we have two rigid insulated tanks here. Initially, 0.79 pound-mole of nitrogen at 2 atmosphere and 460 degree Rankine fills one tank. And the other tank contains 0.21 pound-mole of oxygen at 1 atmosphere and 540 degree Rankine. The valve is open and the gases are allowed to mix until a final equilibrium state is attained. During this process, there are no heat or work interaction between the tank content and the surrounding. Determine first is the final temperature of the mixture in degree Rankine, and then the final pressure of the mixture in atmosphere, and the last one is the amount of entropy produced in the mixing process in BTU per degree Rankine. So the schematic of the system is on the left side. So we have two tanks and then it is connected by a valve here. Okay. So these two tanks are allowed to mix without heat or work interaction with the surrounding until a final equilibrium state is attained. The question is the final temperature of the mixture as well as the final pressure and then the amount of entropy production in the mixing process. And this is the assumption on the engineering model. So the system is taken to be nitrogen and oxygen together. Okay. And then when separate, each of the gases behave as an ideal gas, and then we can also apply the Dalton model here, and then no heat or work interaction occurs with the surrounding, and also we can ignore the change of kinetic and potential energies. And you can see in the schematic on the left side we have nitrogen, on the right side we have oxygen. The initial condition is also given there along with the mass. The first question is the final temperature of the mixture. So we can determine this final temperature from the energy balance with assumption number 4. So it's mean there is no heat transfer with the surrounding, there is no work with the surrounding, and then we can also ignore the change of the potential and kinetic energy. Then the energy conservation equation simplify to be like this. Okay, so Q equal to 0, W equal to 0, and then delta U then equal to 0. So it's mean U2 minus U1 equals to 0. And then the initial internal energy of the system, so this is U1, equals to the sum of the internal energies of the two gases here when they are spread. So in this case we have the contribution from nitrogen as well as the one from oxygen. So it's just the specific internal energy in molar basis times the number of moles of the corresponding gases. And then the temperature of nitrogen is 460 degree Rankine, and then for oxygen it is 540 degree Rankine. So, and then the final internal energy of the system, so this is U2, so this also equals to the sum of the internal energies of the two gases, and it is evaluated at T2, and T2 is what is asked by this question. Okay, so we have this one. And then if we collecting the last three equations, so 1, 2, 3, so you will get this equation. Okay, and the you can see in here we have internal energy in molar basis. It is evaluated at T2 and also evaluated at initial temperature for each gases here. So the temperature T2 here can be determined using the specific internal energy data from table A23E. And again, so we need to do an iterative procedure here, okay, like previous example. And then, however, since the specific heat of N2 and O2 vary little of a temperature for interval between 460 to 540, so in this case, we can assume that the specific heat is constant, and then we will get a simple equation like this one. But in the exam or homework, I will specify clearly, state clearly whether you can assume Cp constant or not. Okay, and then if we assume Cp constant, then you will get this equation. And then selecting value for N2 and O2, you can use table A20E. A20E. Okay, you can open the table here, and then you can use this at average of the initial temperature of the gas. So and the average temperature of these two gas. So we have 460 plus 540, and then divided by 2, you have 500. And then you can get Cv for N2 and Cv for O2 with this one. Okay, and then you just plug in the number, you will get a T2 of 477 degree Rankine. So it's simple when we are allowed to assume a constant Cp. The next question is the final mixture pressure. So we can determine this one using the ideal gas equation of state. So for P2, so it's equal to N time R with over bar. So this is universal gas constants time T2 over V. Okay, so we have T2, and then N is the total number of moles of the mixture, and V is the total volume occupied by the mixture. And then the volume V here is the sum of the volume of the two tanks, right? So we have tank number 1 occupied by initially by nitrogen, and the second tank occupied initially by O2. And then so we can calculate the total tank volume here. This is from the tank that's contain nitrogen initially, and this is from the tank that contain oxygen initially. So N2 is 2 atmosphere. So this is the initial pressure, and then the initial pressure for oxygen is 1 atmosphere. And then if you combine both term here, you will get this one. And then you just need to plug in all the number. You will get P2 of 1.62 atmosphere. The last question is the entropy production due to this mixing process. So this is the entropy balance equation, I believe from chapter 6. Okay, and there is no heat transfer with the surrounding, so it's mean the first term on the right side drop out here. So here we have S2 minus S1 equals to the entropy production, sigma. So the initial entropy of the system, S1, this is the sum of the entropy of the gases at the respective initial states. So we have S1 is the contribution from the nitrogen, and this one is from the oxygen. Okay, and then the final entropy of the system, S2, this is also the sum of the entropy of the individual component, each evaluated at the final mixture temperature and the partial pressure of the component in the mixture. So you have this formula. So keep in mind, to get the entropy, we need two properties. So in this case, temperature and pressure. And then if we collect together this one and this one, you will get this correlation. So sigma equal to this one. This is the contribution from nitrogen, and then this one is from oxygen. Okay, and then once again, if we evaluate the change of entropy in terms of constant specific heat, then you can simplify the equation to be like this one. Okay, and then the required value for Cp, we can get it by adding R to the Cv. So you remember in chapter 3, I believe, Cp equal to Cv plus R. Okay, okay, this one, equation 3.45. And then since the total number of moles of the mixture N is 1, so this is the sum of the mole fraction, the sum of the mole from nitrogen and oxygen. So the mole fraction of the two gases are also 0.79, and for O2 this is 0.21. And then if you substitute this value into the expression for sigma, then you will get this entropy production. So it's positive, so it means the mixing process here is an irreversible process. Next example, this is example 12.6 in the textbook. At steady state, 100 cubic meter per minute of dry air at 30 degrees C and 1 bar is mixed adiabatically with a stream of oxygen, O2, at 127 degrees C and 1 bar to form a mixed stream at 47 degrees C and 1 bar. Kinetic and potential energies effect can be ignored. Determine first is the mass flow rate of the dry air and oxygen in kilogram per minute, and then the mole fraction of the dry air and oxygen in the exciting mixture, and the last question is the time rate of entropy production in kilojoule per Kelvin minutes. This is the schematic of the system. So we have two streams here and then mixed together. So we have first is air, and then the second one we have oxygen along with the given condition here. And then at state 3, after they mix, we have T3 of 47 degrees C and P3 of 1 bar. And then this is the assumption. So this is control volume, operates at steady state, and then no heat transfer occurs with the surrounding, and then we can ignore the effect of kinetic and potential energy. We can also assume there is no work, and then the entering gases can be regarded as an ideal gases. Okay, and then we can also apply the Dalton model, and then the last one here is the dry air is treated as a pure component. Okay, so it's just one component for this dry air. Okay, the mass flow rate of the dry air entering the control volume can be determined from the given volumetric rate. So we have AV at 0.1. So m dot here is AV divided by the specific volume. So in this case, we can use the ideal gas equation of state to estimate the specific volume of the dry air. So T1 is given, P1 is given, and then the molecular weight of air here is 28.97, and then R over bar here is the universal gas constant. So if you plug in all the number, you have this specific volume, and then inserting this number to this equation, you will get m dot A here, the dry air mass flow of 114.29 kilogram per minute. And then the mass flow rate of the oxygen can be determined using the mass and energy rate balance. So at steady state, the amount of dry air and oxygen contained within the control volume do not vary. It makes sense. And then for each component individually, it is necessary for the incoming and outgoing mass flow rate to be equal. So this is for the dry air, and this is for the oxygen. And then for the energy balance, so we assume that there is no work, no heat transfer. We can ignore the impact of the kinetic and potential energy change. Then it is also steady state, so it means this is 0. Then you will have this correlation. So it's mean here you have the incoming energy to the control volume. This coming from stream number 1, stream number 3, and this is balanced by the final energy at state number 3. So m dot A, m dot O here is the mass flow rate of the dry air and oxygen respectively. And then the enthalpy of the mixture at the exit is evaluated by summing the contribution of the air and oxygen each at the mixture temperature. Then you can modify the previous equation to get an explicit form of the mass flow rate for the oxygen as a function of the air mass flow rate and the enthalpy value here. The specific enthalpy can be obtained from table A22 and A23. So A22 for air and A23 for oxygen. Okay, but keep in mind table A23 gives enthalpy value on molar basis. So here the molecular weight of oxygen is introduced in the denominator here to convert the molar value to mass basis. So here you have a molecular weight of oxygen, okay, to convert this value to be mass basis. So you will get the mass of flow rate of oxygen of 23.1 kilogram per minute. And then to obtain the mole fraction of the dry air and oxygen in the exciting mixture, first we need to convert the mass flow rate to molar flow rate using this formula. So just divided by the molecular weight of the corresponding component. So you will get the molar flow rate for dry air of 3.95 kilomole per minute, and this is for oxygen. So N here is the molar flow rate, and then the molar flow rate of the mixture, so this is just N, so this will be the sum of N dot A plus N dot O, so we get 4.67 kilomole per minute. And then we can calculate the mole fraction of the air and oxygen in the exciting mixture. So it's just the ratio between the mole number of dry air over the total mole number of the mixture. So N dot A over N dot, you will get the mole fraction of dry air of 0.846, and this one is for oxygen 0.154. And then the last question, I believe, is the entropy production. So we can apply the entropy rate balance. So this is steady state. So on the left side, this is 0. Okay. And this is the entropy flow. Okay. And the last one here is the entropy production. So the specific entropy of each component in the exciting ideal gas mixture is evaluated at its partial pressure in the mixture and at the mixture temperature. Once again, to evaluate the entropy, we need two properties, and in this case it is partial pressure and mixture temperature. So you have this formula. And then sin P1 equal to P3, I believe it is 1 bar, the specific entropy change of the dry air. So P3 equal to P1, and then you can have this equation. So this is SA at T3, and then partial pressure at 0.3, and then minus SA at initial state. Okay, you have this one. Okay, and then this one equals, so it's mean it's 1, and then you get this one. And then the S degree of the dry air can be obtained from table A22, and then since P2 equal to P3, then you can also make a simplification. So you will get this formula, and then we can use table A23 to get S degree for oxygen. Okay, and I believe you just need to plug in number and then make some simplification, and you will get this entropy production. So okay, so repeat this example by yourself, plug in the number, and then follow step by step until you understand each steps and that you are ready when this type of problem come into the exam.